Hello everyone, today we are going to be covering Chapter 5, Lesson 2. This is on Calorimetry and Enthalpy, Parts 1 and 2. So this lesson is one of the more easier ones and requires only a little bit of math. So let's get started. So Part 1. What factors involve heating a substance? There are three factors that involve heating a substance. The first one is temperature. Temperature is the measure of the average kinetic energy of a system. Second, we have the mass. The mass affects the amount of heat a substance can absorb or release. And finally, we have the specific heat capacity, and that is the thermal energy needed to raise the temperature of 1 gram of a substance by 1 degrees Celsius. A higher specific heat capacity indicates a longer heating and cooling time. So pretend you have a piece of metal and you have its mass in grams. So the specific heat capacity tells you how much energy is needed to make the temperature of this substance go up by 1 degree Celsius. So you have to remember the specific heat capacity of water, as it will be used in basically every calculation you have. So calorimetry. So what is calorimetry? Calorimetry is the study and technology of measuring thermal energy during physical and chemical changes. A calorimeter is a device that measures the change in thermal energy, and it consists of a thermometer, isolated systems, and water. So there are two types of calorimeters: a constant pressure calorimeter, which can also be a coffee cup calorimeter, or a constant volume calorimeter, also could be a bomb calorimeter. So how does a calorimeter work? So let's start with the coffee cup calorimeter. So a mass of water is put inside a styrofoam cup that is then placed into another styrofoam cup. The substance will be placed in the water, with the water acting as the surrounding. This will monitor the energy change. Now the water and substance are completely isolated by the styrofoam cups. So this is a fully isolated system. So next, the initial temperature of the water will be measured, and then the final temperature will be measured after the process takes place. The water must be stirred in order to have a balanced distribution of energy throughout the system. The coffee cup calorimeter is useful in measuring changes in heat during neutralization reactions, dissolving, and cooking. So next, let's go with the bomb calorimeter. So bomb calorimeters are used specifically to measure heat changes in combustion reactions. The reactions happen inside a metal chamber filled with oxygen. This is called the bomb. The reaction starts with the substance being ignited by an electric coil, and then the bomb is surrounded by water, which absorbs the energy from the reaction. Okay, so let's start with the calorimetry calculations. Q is equal to mCt. So Q is the heat energy in joules. M is the mass of a substance measured in grams. C is the specific heat capacity measured in joules per gram degrees Celsius. And T is the change in temperature in degrees Celsius. So let's do a unit analysis here. So since Q is equal to joules, then we must know that M, C, and T multiplied together must make joules. So here we have grams and degrees Celsius, and we're multiplying those to joules per gram degrees Celsius. So with grams canceling with grams at the bottom, and Celsius canceling with Celsius at the bottom, we are just left with joules. This is important information. If the calculated heat energy, Q, is negative, the system loses energy, therefore an exothermic change. If the calculated heat energy is positive, the system absorbs energy, therefore an endothermic change. So let's use this example of fire. So if Q is negative, the system is losing energy, therefore an exothermic change. This is shown by the fire, as the fire is transmitting this energy to the surroundings. Fire is losing heat and giving it to the surroundings. Now for the endothermic part, we have an ice cube. So the heat energy Q is positive, so the system is absorbing energy, therefore an endothermic change. So an ice cube is melting because it is absorbing heat from its surroundings. Okay, let's start with the calculation portion of the lesson. So example 1. A student places 50 milliliters of a liquid water at 21 degrees Celsius into a polystyrene calorimeter. She places a sample of silver at 100 degrees Celsius in the calorimeter. The final temperature of the water is 21.33 degrees Celsius. The specific heat capacity for water is 4.18 joules per gram degree Celsius, and the density of the water is 1 gram per milliliter. How much thermal energy was absorbed by the water in the calorimeter? So first, let's understand what we're looking for. What we're looking for is Q. So now that we know what we're looking for, let's list down the information that we have. So we are given the volume of the water. So volume was equal to 50 ml. So we want this in grams because we cannot use volume to solve for Q. So let's use the density formula to solve for the mass. So density is equal to mass over volume, and now mass is equal to density times volume. So let's put in our information. So we're given mass is equal to the density, which was 1 gram per milliliter, multiplied by the volume, which was 50 ml. So our mass is 50 grams. Next, we were given the specific heat capacity for water. So C was equal to 4.18 joules per gram degree Celsius. And now the temperature. As you can see, it states that the final temperature of the water is 21.32 degrees. So our T final was equal to 21.33 degrees Celsius, and our initial was given at 21 degrees Celsius. So 21 degrees Celsius. So let's go to our equation now. Q is equal to mass times the specific heat capacity times the change in temperature. So it's already arranged to solve for Q, so all we have to do is sub in our values. So Q is equal to the mass, which was 50 grams, multiplied by the specific heat capacity, 4.18 joules per gram degree Celsius, and then the change in temperature, which is to be the final temperature minus the initial temperature. So it's going to be 21 degrees Celsius minus 21.33 degrees Celsius. So if you plug this into your calculator, you should have gotten 68.97 joules. So here's your answer. So therefore, the water absorbed 69 joules. Okay, example 2. A piece of metal with a mass of 14.9 grams is heated to 98 degrees Celsius. When the metal is placed in 75 grams of water at 25.5 degrees Celsius, the temperature of the water rises to 28.5 degrees Celsius. What is the specific heat capacity? So, the specific heat capacity pertains to the metal. So, what is the specific heat capacity of the metal? So, this question is a little bit more complicated, as we're going to have to find this the the heat gained by the water in order to find the specific heat capacity of the metal. So by reading this problem, we can already find that this question is heat losing, or the metal losing heat. So this is overall a exothermic reaction. So let's list down what we were given. So let's start with the metal. What we were given from the metal. So we were given the mass of the metal. So M of metal was equal to 14.9 grams. Next, for the water, we're given its mass as well, which was 75 grams. So mass of water is equal to 75 grams. Okay, so now we are also given the final temperature of both, which was 28.5 degrees. So we can write that down for both. So T final is equal to 28.5 degrees Celsius, and T final is equal to 28.5 degrees Celsius. Now this is where they differ. They differ in their initial temperature. So the metal started off with the initial temperature of 98 degrees. So T initial is equal to 98 degrees. And then for the water, it was T initial is equal to 25.5 degrees. So we have all this information, but there's one thing that we're missing: the specific heat capacity. Well, you see, we always have the specific heat capacity of water. C is equal to 4.18 joules per gram degree Celsius. So now we are able to solve for the specific heat capacity of metal, as we have all the information we need. So, step 1, we are going to solve for the heat energy of the water. So Q of water is equal to M C change in T. So we're just plugging this value in, all the values that we have in. So the mass we're given 75 grams. Specific heat capacity of water 4.18 joules per gram degree Celsius. And then the change in temperature. So T final 28.5 degrees Celsius minus T initial 25.5 degrees Celsius. So the Q of water is equal to 940.5 joules. So this is very important to solve for metal, because the Q of water is equal to the negative Q of the metal. Why is this? Because the water is absorbing energy from the metal that is losing energy, since it is an exothermic reaction. So knowing that, now we have all the information we need to solve for the specific heat capacity of the metal. So Q metal is equal to MC change in T. Okay, so now what we're going to do here is we know, now since we know all information, all we have to do is isolate for the specific heat capacity. So C is equal to Q of the metal divided by the mass and change in temperature. So let's plug in our values. C is equal to, now we know that this is negative 940.5 joules divided by the mass. Mass is equal to 14.9 grams, and the temperature, which is in the final minus initial, so 28.5 degrees Celsius is the final, and the initial was 98 degrees Celsius. Plug this into your calculator, and the C of the metal, C metal, is equal to 0.9908 joules per gram degrees Celsius. So here's your answer. Therefore, the specific heat capacity of the metal is 0.908 joules per gram degree Celsius. Okay, let's continue on with part 2. Enthalpy. All substances undergoing chemical or physical or nuclear change hold a certain amount of thermal energy. The total amount of thermal energy is called enthalpy. So it is almost impossible to measure the actual amount of thermal energy in a substance. However, the change in enthalpy can be measured using calorimetry. So the change in enthalpy is equal to the enthalpy of the products minus the enthalpy of the reactants. So it is very important that the change in enthalpy can be measured using calorimetry, because in this case, the change in enthalpy, change in H, can also be equal to Q, which is the heat energy. So when the change in enthalpy is greater than 0, so when it is a positive number, the system absorbs thermal energy from its surroundings. This means that an endothermic reaction occurs. When the change of enthalpy is less than 0, so a negative number, the system releases energy to its surroundings. Therefore, an exothermic reaction occurs. So, molar enthalpy change. Molar enthalpy change is the amount of energy change per 1 mole of a substance that undergoes a physical, chemical, or nuclear change. So the change in enthalpy is equal to the amount of moles of a substance, N, multiplied by the molar enthalpy change. So here are the different types of molar enthalpy change. So we have the change in molar enthalpy of Sol, which is change during dissociation, molar enthalpy of change of Com, which is the change during a combustion reaction, molar enthalpy of change VAP, which is the change during evaporation, and molar enthalpy of change of form, which is the change during the formation of a compound, and finally the molar enthalpy of change neutralization, which is the change during a neutralization reaction. So these do not affect the equation, as this only tells you what type of reaction is happening. Okay, let's tackle this problem. If a 1 gram sample of ethanol is spread across the skin and evaporated, what is the expected enthalpy change? the molar enthalpy of vaporization is equal to 38.6 kilojoules per mole for ethanol. Okay, so let's start with knowing what we want to find. So what we want to find is the enthalpy change. So pretty straightforward, finding this. Okay, so let's see what we're given. So we are given the mass of ethanol, which is equal to 1 gram. So what we need is the number of moles, because that is what we need to solve for the molar enthalpy, or the enthalpy change, because enthalpy change is equal to the number of moles times the molar enthalpy change. Okay, so how do we find this? Well, first we need to know what is ethanol. Ethanol is CH3 CH2OH. So knowing this, now we can use the formula. Number of moles is equal to mass over molar mass. So you need to get the molar mass of this using the periodic table. So the molar mass of ethanol is equal to 46.07 grams per mole. So we plug this all into our equation. Number of moles is equal to 1 gram over 46.07 grams per mole. So these cancel out, and we are given 0.0217 moles. Okay, so now that we have all this information, we can now use our formula. So enthalpy change is equal to the number of moles times the molar enthalpy of vaporization. So it's already arranged to solve for H, so we just need to plug in our values. N is equal to 0.0217 moles times 38.6 kilojoules per mole. So moles cancel out moles, and so our answer is going to be 0.838 kilojoules. Now all we have to do to convert this into just joules is multiply it by 1,000. Sorry. So change in enthalpy is equal to 838 joules. Okay, so how can you represent whether a chemical reaction is endothermic or exothermic? So there are two ways. So the first way is through a thermochemical equation. So the way you write this is, so let's take magnesium oxide as an example. So the formula for magnesium oxide is 2 Mg plus O2 is equal to 2 MgO. So how do we put the energy into this? Like, is this exothermic or endothermic? Well, you see, this will be a exothermic reaction, and so here is how we will write it. If it's an exothermic reaction, we will put energy on the side with the products plus energy, and this energy can either be given to you as just energy, or it will given to you as a value. If you want it to be if we do the reverse, 2 MgO turns into 2 Mg plus O2. Here, if we put energy on the side of the reactants, then this will become a endothermic reaction. So this side right here, exothermic and endothermic. So remember this rule. If energy is put onto the side of the products, it is an exothermic reaction, and if energy is put onto the reactant side, it is endothermic. Okay, here's another way that it can be written. So let's take the same example, magnesium oxide. Mg, 2Mg plus O2 turns into 2MgO. Here it can just say change in enthalpy is going to be negative energy. So what this means is that if it's negative, energy is exiting the system, meaning exothermic. So this equation right here is equal to this one. Now, the same thing goes with the endothermic. 2MgO turns into 2Mg plus O2. So here, energy is going to be a positive value. So when energy is a positive value, that means that the system is gaining energy. So this here is equal to this one, and therefore it is an endothermic reaction. Okay, now let's go through to the second way to represent a chemical reaction as endothermic or exothermic. So the other way is a potential energy diagram. So how do potential energy diagrams work? Okay, so let's start by making a graph. So on your y-axis, you have the potential energy. And on your x-axis, you have the reaction progress. So, let's say for example, we are given the exothermic reaction of Mg plus O2 turning into MgO. So here, we know that it starts with high energy, and then it drops down because it's an exothermic reaction. From here, it just continues. So here, this is the change. It's equal to negative energy. And we have our Mg plus O2. So these right here are our reactants. And as the reaction progresses, the energy change is negative, and then the product of MgO is created. So this diagram is an example of a exothermic reaction. Now let's look at the opposite, the endothermic. So we make our same graph. This time we start with low energy, then it shoots up, and there we go. So here we have MgO. Here is a change in enthalpy, which is going to be now positive energy. And then we are given our products, which is Mg plus O2. So now here we have our reactant, and here we have our products. So as you can see here, the potential energy for the exothermic decreases, while in the endothermic, the potential energy increases. So here are the two ways to represent a chemical reaction, if it is endothermic or exothermic. Okay, let's practice the first way. So the combustion of methane, CH4, is an exothermic reaction. When 1 mole of CH4 burns, 802.3 kilojoules of energy is released. Write the thermochemical equation in two different formats. Okay, so when combustion happens, we know so it's CH4, methane, is combusting, so plus O2, and it becomes CO2 plus H2O. And obviously we need to balance this, so we need 2 H2O, 2 O2. Okay, so now that we have the balanced chemical formula, we need to write it in two different ways. So the first way we can write this is going to be into the equation, adding the energy into the equation. So here it says 802.3 kilojoules of energy is released. So when it says released, that means it's an exothermic reaction, because energy is released, heat is going to the surroundings. So CH4 plus 2O2 becomes CO2 plus 2H2O plus the energy, 802.3 kilojoules. Now the second way to write it is outside of the equation, which is the second way I showed you guys. So CH4 plus 2O2 becomes CO2 plus 2H2O, and then we just write it here. Change in enthalpy is equal to negative 802.3 kilojoules. So these two here are the same. So these two mean the same thing but are written differently. Okay, so now let's do the second way to represent if it's exothermic or endothermic. So it says here, draw a potential energy diagram for the reaction of CaCl2 plus CaCl2. Okay, so what we are doing here is, first let's make our diagram. Of course, you gotta label it potential energy and then reaction progress. So the change in energy given to us is negative. It's a negative value. So this means that it's exothermic. So what we want to do is start with a high potential energy, and then we want to go down to show that that change in energy is down and that it lost energy. The system lost energy. From there, the reaction continues. So CaCl2 solid becomes CaCl2 aqueous with a change of negative 82.8 kilojoules. Okay, now let's go to the second one. Draw a potential energy diagram for the reaction of CO2 solid plus 20.3 kilojoules making CO2 gas. Again, make our diagram, label, and now let's see. So in this equation, we're given the energy on the reactant side. So again, what does this mean? This means that it is an endothermic reaction. So let's start with, we're starting with the low potential energy, and then we're shooting up to show that we had an increase in heat energy, and then the reaction continues. So here we have CO2 solid, we have a enthalpy change of positive 20.3 kilojoules, and then we have the product CO2 gas. So there you go. This is how you do it the second way.